Hi, this is the AP Calculus lesson from, I think, April 10th. And what I'm doing here is going over some related rates problems, which is something that we have skipped in the past. This is from April 8th posting, and it's called Related Rates Worksheet. It says easy goes with card game. So that's what this is. And if you have not looked at the lesson from Wednesday, you should look at that and go through some of the cards. There's also an answer key on Classroom, and like fast forward through that lesson so you have an idea what we're doing, because that was like the build up to this. So this problem says air is being pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. At what rate is the radius increasing when the diameter is 20 centimeters? So words like that are some of the clues that you're in a related rates problem. It says, at what rate is the radius increasing when the diameter is 20 centimeters? So it's giving you conditions. And they're not giving you an explicit or a specific rate formula. So this is kind of a setup that I like you to use at first when you're learning these. You're going to draw a picture, and then actually the next thing after the picture is to do the given rates and the constants, then do the find, and then the last thing is the equations and relationships. Okay, so picture is first, then the given rates and constants, then what you're supposed to find, and then the equations and relationships. So we're going to start with the picture. And hopefully you have this worksheet someplace where you can see it. If you're lucky, you were able to print it out. And so it says that air is being pumped into this balloon at a rate of 20 centimeters or 5 centimeters cubed per minute. And so I'm going to just draw a picture. Here it is, a very straightforward sphere. I usually do something like an arrow, maybe a double arrow, to indicate something's going in. And so I'm going to write the rate next to that. So again, if air or water is being added to something, that's volume. And they actually gave us the rate of the volume change. And they said it's 5 centimeters cubed per minute, right? And I'm going to mark this on my picture. That's the only rate they gave us. And you're like, wait, what about that diameter 20 seconds? No, because that's only at a specific time. So in the picture, you just write the situation, nothing specific that relies on a certain time. So then when they ask you for the given rates and things, the only thing that was given that is always the same across the whole problem is that dV/dt is 5 centimeters cubed per minute. I'm not sure why it's flashing like this, but I'm just going to stick with it because I haven't been able to fix that this morning. And then they wanted to, you're supposed to write in what it is that you're supposed to find, and like at what time are you supposed to find it. So the problem is asking at what rate is the radius increasing. So we're supposed to find dr dt when, and this will catch up with me in a second, find dr dt when the diameter is 20. And by the way, the diameter is 20. When we're dealing with all of our circle formulas and spheres, we're always dealing with radius, right? So I'm just going to put that would also be the same as radius equals 10. So the next thing they want you to do is talk about, what are the relationships or equations that you can use? Well, it makes sense to use volume because they're giving me information about volume, and I'm going to be looking for radius. And since the volume formula for a circle uses radius, I'm going to get dr dt by using volume. So I'm going to do the equation. I'm going to start with volume equals 4/3. That's a 4/3. This is volume of a sphere, pi r cubed. And one thing to watch out for is you would never plug anything in here unless there's something in the problem that never changes according to time. So you can't plug the radius in here because the radius changes according to time. So this radius is always going to be getting bigger and bigger and bigger. So you can't plug in this 10 yet. We're not going to plug in the 10 until we're ready to solve for drdt. And we don't have a drdt, so we can't plug in the 10 yet. And then you might say, oh, shouldn't I put in the 5 centimeters for dvdt? No, because this is v that we're looking at now, and you want dvdt. So we're going to take a derivative. And if you were in class or watched last class's video, you know that we're just going to do dv/dt, and we're using explicit differentiation. 4/3 pi, okay, that's a constant. I mean a coefficient. So 3 times 4/3 pi would give me 4 pi, and then r squared dr dt. Boy, this is driving me crazy. Right, so that's my derivative. And now, if you're lucky, you can plug in and solve once you have the derivative. Now, they're not always this straightforward, but man, when they are, it's really nice. So what you would plug in here, because now we have everything we need, is you would plug in the volume, the dv/dt, sorry. And we know that, and I'm going to try this with units. We know that dv/dt is 5 centimeters cubed per minute. And then equals, we've got 4 pi r, r squared. Let's plug in the r squared. So if I plug in, that would be 10 centimeters, and I'm going to square it. And then I'm looking for dr dt. And by the way, if you think about it, we already know the units of dr dt, right? Radius is linear, so radius is a line. So that's going to just be centimeters and per minute. So our units should work out to be centimeters per minute. And if you don't want to include units when you do these problems, that's completely fine. Sometimes they get too gnarly for that. So I'm going to go ahead and multiply this out. So that's going to get me 400 pi centimeters squared dr dt. Let me write that a little easier. Equals 5 centimeters cubed per minute. Then I'm going to divide both sides by 400 pi centimeters cubed. Or squared, sorry. And that wasn't per minute. And then you'll see that this will simplify to 1/80 pi. Most of our units cancel, and I end up with centimeters per minute, which is exactly what I expected for dr dt. Again, you don't have to follow the units through the problem if you don't want. You can put the units on at the end if that's helpful for you. And I think I'm going to stop here at the end of this problem and then just make this into more than one recording, because this is really driving me crazy that it's stopping and starting.